So we know that hydraulic conductivity changes with fluid properties, but intrinsic permeability does not. So let's take a look at how hydraulic conductivity might change with temperature. And for this example, we'll use a groundwater system that changes quite a bit in temperature, and this is a geothermal reservoir. So this geothermal reservoir cools from 93 degrees C to 66 degrees C. And it has an intrinsic permeability of 1 millidarcy. And we want to know what that hydraulic conductivity is going to do when that temperature changes. So when I looked up the fluid properties, and at 93 degrees C, we have a density of 963 kilograms per cubic meter and 2.97 times 10 to the minus fourth kilograms per meter second. At 66 degrees, we have 980 kilograms per cubic meter, and we have 4.16 times 10 to the minus fourth kilograms per meter second. So that represents about a 1.8% increase in density as the temperature decreases, but a 40% change in viscosity as the temperature decreases. So this is pretty much what we need to get started. We also need to know that 1 darcy is equal to 9.87 times 10 to the minus 13th meters squared. So we'll be able to convert our units in darcies to meters squared, where we can cancel out our units. So what do we know? Well, we know the relationship between hydraulic conductivity and intrinsic permeability, right? We know that the hydraulic conductivity is the intrinsic permeability times the density times the acceleration due to gravity divided by the viscosity. Excuse me. Divided by the viscosity. So let's go ahead and convert our units of intrinsic permeability from millidarcies. So we got 1 millidarcy times, there's obviously 1,000 millidarcies in 1 darcy. And we multiply times 9.87 times 10 to the minus 13th meters squared per 1 darcy. So these darcies cancel out and the millidarcies cancel out. And we end up with an intrinsic permeability of about 10 to the minus 15th meters squared. Let's go ahead and calculate our hydraulic conductivity at those temperatures. So K at 93 degrees C is going to be equal to our 10 to the minus 15th meters squared times 963 kilograms per cubic meter times 9.81 meters per second squared. And that's divided by our viscosity, which is 2.97 times 10 to the minus fourth kilograms meters second. So we can see that our meters go out, our kilograms go out, one of our seconds goes out, and we end up with 3.2 times 10 to the minus 8th meters per second. So then our hydraulic conductivity at 66 degrees C is equal to 10 to the minus 15th meters squared. So the intrinsic permeability, of course, hasn't changed, same reservoir, just a property of the reservoir itself, not the fluid, times 980 kilograms per cubic meter density times 9.81 meters per second squared divided by, now we have 4.16, 10 to the minus fourth kilograms per meter second. And that comes out to be 2.3 times 10 to the minus 8th meters per second. All right, so these are our two hydraulic conductivities. So the change in that hydraulic conductivity is not as much as the change in the viscosity, because we have our density change is increasing by 2% and our viscosity is changing by 40%. So the overall change is a little bit less. So we have a decrease in hydraulic conductivity of about 25%. Okay? So we wouldn't expect a big change in a groundwater system because groundwater systems don't change much. It'll change maybe just a few degrees Celsius. Only where we have big changes in temperature will this be an issue, or if we have different fluids where we have big changes in density or viscosity, would we expect there to be a change in hydraulic conductivity, which is why we can usually get away with hydraulic conductivity instead of intrinsic permeability to describe aquifers.